Hey guys, I'm Jay. Today is my LeetCode review one take vlog on 530th problem. Minimum absolute difference in binary search tree. We are given the root of a binary search tree. We will return the minimum absolute difference between the values of any two different nodes in a tree. Let's see the example 1 here in this binary tree. And the final output is 1. As we can see, 1 to 2, 2 to 3, and 3 to 4. The minimum difference is just 1. Then, let's get started with our intuition to solve the problem. And there is an important property of binary search tree that we should know. If we perform an in-order traversal of a binary search tree, the node values will be visited in sorted order. And the minimum absolute difference between any two nodes will always occur between two consecutive values in the in-order traversal of the binary search tree. So we'll perform an in-order traversal to retrieve the node values in sorted order. In-order traversal. Then we compute the absolute differences between consecutive values. Next, we'll keep track of the smallest difference we encountered during the traversal. Then let's get started with the easy solution 1 here. In this solution, we store the node values in a list during the in-order traversal. Then we compute the minimum difference. So the first line of the code is list of integer with values. We assign a new array list to it. Then we declare and call our in-order traversal method. In-order traversal method. And this method takes two parameters. First is the root, second is the value list. Then we just compute the minimum absolute difference with a for loop. First, let's declare our variable to store the minimum difference. And we assign our integer dot max value to it. Next, we create a for loop. And there's one thing we need to pay attention. The current I was started at 1. So we can avoid the index out of bounds exception. And the condition is I should be less than values.size. Because values is a list, not an array. And we'll increment I after each iteration. And inside the iteration, first, we need to update the minimum difference with math.minimum method of mean difference. And the new minimum difference, which is values dot get I minus values dot get I subject 1. And out of the for, we just got the minimum difference that we need, so we just return the variable. Second, we need to declare and implement the in-order traversal method. First, private void in-order traversal with two parameters. First is the tree node, and second is the values. List of integers. Let's call it values. And inside the method body, first we'll check if the node is null. If node is null, we just end this method. Then we'll recursively check the left subtree, then with the current node, and recursively check the right subtree. In-order traversal with node.left, which is the left subtree, with values list. Then we'll visit the current node. So we add a node's value into the values list. Values.add with node.value. Then we'll recursively check the in-order traversal of node dot left, node dot right, which is the rest subtree, and the values list. And that's our code. Let's submit code and check for correctness. Then we will analyze the time and space complexity. Oops. As the method is void, so we'll return nothing. So for the time complexity, the in-order traversal visits each node only one time. So it is big O of n. And we're calculating the difference takes big O of n too, so the overall time complexity, it is big O of n. Yes, our code got accepted. And for the space complexity, we stored all nodes values in the list, which is big O of n. And we did another recursion stack for in-order traversal of big O of h. So the overall space complexity is also big O of n. And this is the first solution. So, and we can come up with another better solution. And we don't need a list, we just use some optimized method. Then let's get into the second solution, optimize in-order traversal without extra storage. And at the very beginning, we also have to create several member variables. For example, private int mean difference started at integer dot max of value. Then we'll create another variable called previous value. So we can check the previous node value during the traversal and calculate the difference on each state. Private integer of previous value. And there's one thing important. It started at null because for the first method, this method doesn't have its nearby node. Oh, sorry. This node doesn't have a nearby node on its left side. Then inside the get minimum difference method, first we'll call in-order traversal method. In-order traversal method with the root node. Then we just return the minimum difference. As all the logic will be implemented inside the in-order traversal method. Then we'll implement the in-order traversal method. In-order traversal method with the node. The very first state, we still have to check if node is null. If so, we just return. Next, we'll visit the current node if the previous value is not null. If previous value is not equal to null, then we'll update the minimum difference variable. Minimum difference variable equals math.min with the minimum difference itself and a new minimum difference, which is node.value minus previous value. Then we'll update the previous value with node.value. At this moment, previous value equals node.value to prepare for the next iteration. Then we'll recursively call the right subtree. Oops, there's one thing we forgot. We have to recursively check the left subtree before we visit the current node, which is here in order traversal with node.left. And we'll check the right subtree at the end. And that's our code for the optimized solution 2. Let's submit code and check for the correctness, and then analyze the time and space complexity. Yes, our code got got accepted. So the time complexity, it is also big O of n as we visit each node only one time. But for the space complexity, first, we have no additional storage for values. We only create a constant variable to store the previous value. So this is big O of 1. And we use another recursion stack for the in-order traversal, which is big O of h. H is the height of the tree. So the overall time, the space complexity, it is big O of h. And that's the second solution. But there is a best solution in the world. We don't need any extra space. We only need big O of 1 space complexity to achieve this problem. So let's get into the third method, which is the Morris in-order traversal. So the main idea is this algorithm will modify the tree temporarily during the traversal, and it doesn't have to change the structure of the tree, and it would remove the temporary links during the process. Then let's get started with the third solution. First, we still have to create a previous variable here, which is integer here with previous started and now. Then we create a minimum difference started at integer dot max value. Next, we'll create a tree node variable called current starting at the root node. Then we'll begin the Morris in-order traversal. While the current node is not equal to null, we'll keep this loop. First, we'll check if there is no left child. If so, we'll process the current node and move right. If current dot left is equal to null, then we'll check if the previous value is set or not. If yes, we'll update the minimum difference. If previous is not equal to null, then we'll calculate the new minimum difference with the previous value, which is min difference equals math.minimum method with minimum difference itself and current node.value minus subject previous value. Then we'll update the previous value to the current node's value. Previous value equals to the node current node.value. And then we'll move to the right subtree. Current equals current.right. And on the other hand, if the current.left subtree is not equal to null, then we'll find the in-order predecessor of the current node. So the code is, first, we'll get the in-order predecessor node of the current node, which is tree node with predecessor equals current.left. Then we'll create a while loop to check if the predecessor.right subtree is not equal to null and predecessor.right is not equal to current. Then we'll navigate to the rightmost node of the left subtree, which is the rightmost node in the left subtree. So the code is while predecessor dot right is not equal to null, and predecessor, but right is not equal to current. If so, we'll update the predecessor with its right subtree. Predecessor equals predecessor dot right. Then we'll check if the right child of the predecessor is null or not. We'll establish a temporary link to backtrack without extra space. If predecessor dot right equals null, then we'll create a link which is predecessor dot right equals current. So we link these two nodes. So we don't need any extra space to backtrack into the current node. And then we'll move the current node into its left child to continue the traversal. Current node equals current dot left. And on the other hand, if the right subtree of the predecessor is now equal to null, then which means the thread already exists. It means we have finished the left subtree. So we'll remove the temporary link to avoid endless loop. Predecessor dot right equals null. And then we'll check if the previous value is not equal to null. If so, we will update the minimum difference with math.min with mean difference itself and current dot value subtract previous value. Then we'll update the previous value to the current value to prepare for the next iteration. Previous equals current dot value. And then we'll move to the right subtree after finishing the left subtree. Current node equals current dot right. And out of the while loop, we just return the minimum difference that we wanted. Then let's download the code and check for the correctness. Yes, our code got accepted. And for the time complexity, it is also big O of n, as each edge in the binary search tree is traversed at most twice. Once we are going down and once is coming back up. So the overall time complexity is big O of n. And n is the number of nodes in the tree. And for the space complexity, it is the best algorithm, which is big O of 1. This is because the Morris in-order traversal creates a temporary right pointers from nodes in order predecessor back to the node itself to backtrack without a stack or recursion. So, and the tree is modified temporarily, but restored to its original form. So there is no additional space is permanently consumed. And thank you guys for watching. This is the 3 solutions for the minimum absolute difference in binary search tree problem. You can also visit my GitHub repository here, which contains all the codes and notes to build this online GitHub page. And inside the GitHub page, you can see all the problem description, intuition, and code solution with very detailed explanation and the final time and space complexity analysis. And thank you guys for watching again. I'll put those 2 links on my YouTube description below. And I'll see you next time. Bye bye.